Good afternoon, everyone, and thank you, Paul, for introduction. Today I'm going to talk about angle decomposition methods for wave equation migration. Wave equation migration and reverse time migration use the full wave equation as opposed to Kirchhoff migration. These migration techniques can handle multiple propagation paths and thus image complex structures. Conventional common image gatherers, CIGs, from Kirchhoff migration suffer from artifacts due to multipathing. Thus, constructing angle gatherers from wave equation migration, we can successfully avoid these artifacts. And these angle gatherers also offer other advantages over conventional CIGs, such as direct replications for amplitude variation with angle and azimuth, for example. One of the current industry challenges is imaging subsalt. For example, this model was derived from the 6B model, and it contains a large salt body that will triplicate the waves as they pass through the salt due to the high impedance of the salt body, and create challenges in the subsalt region highlighted by the yellow box. So the motivation for my work was to compare the methods as they apply to imaging in complex geological structures. And there have been different methods proposed to address angle domain imaging problems. In this talk, I will discuss only two methods and their applications to complex structures and comparison in cost. So the two methods are Tony introduced the methods, and the first method is a direct decomposition of seismic wavefields using the Poynting vectors. And alternative method is in the image domain, using the extended images. Decomposition using slant stacking, or a radial trace transform in the Fourier domain. And the labels you'll see in my presentation are PV for the Poynting vector and EI for the extended images. So in the first method, we compute the Poynting vectors of the source and receiver wavefields as we extrapolate the wavefields in the subsurface. We do the computations on the fly. And the Poynting vector is the power flux vector, and it points in the direction of energy propagation. Thus, we can extract the angles of reflection and azimuth at each image point using the Poynting vectors. For the acoustic waves, we can do this by calculating the pressure wavefield and multiplying by the particle velocity, extract it on the fly as we propagate the wavefields. For each shot. And for example, this snapshot is one snapshot in time of the source wavefield. And the source is represented by the red dot on the surface. When we plot the Poynting vectors of the source wavefield, you see that the vectors are normal to the wavefront, and the amplitude varies. This causes a problem for the angle computations, because the amplitude variation of the vector is twice the dominant seismic frequency. So each component of the vector, the x, y, and z components, will go through 0. And this is shown on the next slide. So this picture shows just the x component of the Poynting vector. And the white color represents energy traveling to the left, and the black color represents energy traveling to the right. And the gray color means 0. So as we can see that in the middle of the wavefield, the x component is 0 because the Poynting vector is normal, is oriented vertically, as expected. But we also have this troubling 0 amplitude along the wavefront, indicated by the red arrow. And same happens for the z component and the y component. And this is a snapshot of the receiver wavefield, and propagating back to the surface of the where we have the receivers. So plotting the Poynting vectors, again, you see the amplitude varies rapidly, and the x component again suffers from the 0 amplitude in the middle of the wavefront. So one way to avoid 0 amplitude is to smooth the Poynting vectors in space and time. So the square bracket represents smoothing, and the capital X and capital T are our window sizes. And we have to be careful by choosing correct window size, because we don't want to over-smooth. But when we smooth enough, over here again is the x component of the source Poynting vector. You see that we avoid division, we avoid the zero amplitude of the Poynting vector for the source and the receiver wave fields. And zero amplitude will cause troubles because we want to normalize our Poynting vectors. So we want to avoid division by zeros. So pictorially, we can represent the extraction of the angles after we obtain the Poynting vectors and smooth them and normalize them. So PS and PR are the Poynting vectors of the source and receiver wave field. The hats represent normalization by their amplitudes. So the angles we're interested in are the reflection angle theta. Here's 2 theta is the angle between the Poynting vectors from the source and the receiver side. And the azimuth is computed by projecting the difference of the vectors onto the xy plane and computed the angle from the reference. In this case, I choose the x-axis, or unit vector I points in the x-axis direction. So here's the little bit of math. So the dot product between the Poynting vectors gives you 2 theta, and a dot product between the unit vector along the x-axis and the projection of the difference between the vectors give you the azimuth. And the final product, the angle gathers, are obtained by summing the image contribution to appropriate angle bin. Okay, in the alternative method, we use extended images. This method is an image domain method. And in summary, we have to compute extended images first, and then convert them to reflection and azimuth angles by using slant stacking. And we do that after stacking over shots to save the cost. And I'll go through some details. So first step is to go to image domain. For example, this formula shows you conventional cross-correlation image and condition formulated in frequency domain. And the output of this operation is image as a function of space, x, Rx. This is a special case of the extended or generalized image and condition, and where we preserve the cross-correlation space and time lags. So the output of this operation will be a 7-dimensional extended image, R as a function of space, space lag, and time lag. So fortunately for the angle computations, we can use as a subset of the extended images, just the space lag gathers, for tau equals 0. And by using slant stacking, we transform the offset, the subsurface offset axis lambda, into the angle axis, theta and phi, by looping over all possible angles and obtaining the angles. So here's the move-out function that Tony discussed before me, which represents the reflection event in the CIGs. And unit vector Q contains the azimuth. And the second equation, n dot lambda, helps us to save some cost because we can use the reflected normals instead of computing one of the lags. Okay, so and after we do this, we obtain the angle gatherers, like before. So compute the extended images, slant stack in that space to compute the angle gatherers. So now I summarize the 2 methods. I want to see how they apply to imaging in complex media. And the way I do this is by using 5 different criteria. The first 2 are related to the cost, the wave reconstruction cost, and the application of the Poynting vector or the extended imaging condition. And the last three relate to the complex media. So the angular resolution. How well resolved are the angle gatherers? Can we obtain a specular reflection, or is it smeared? And can we apply this method to locally heterogeneous media and media characterized by multiple propagation paths? So if you have multipath, we would like to capture all propagation directions, all illumination angles. So that's going to be important. Okay, so the wavelet reconstruction step is the same for the two methods, except for the point-in vector calculation. We also require computing the velocities to obtain the point-in vector direction. So the cost is going to be cheaper for the extended imaging method, as indicated by the check mark. And however, the imaging condition cost for the extended imaging method is going to be far larger than for the point-in vector, because we have to compute the cross-correlation lags and save them. So that's one of the main disadvantages of this method, the computational cost. And like I mentioned before, the point-in vectors are computed on the fly as we propagate the wave fields. So it's fairly cheap. So the point-in vector is cheaper for the imaging condition. So now, angular resolution. The point-in vector, one of the biggest assumptions I make is the specular reflection for the point-in vectors. So we only obtain two vectors at each image point, and then compute the angles using those point-in vectors. So the resolution is really good for the point-in vector. But the resolution for the extended imaging method is related to the extended space lag gatherers and how we do the slant stacking. So for example, let's look at the 6D model I introduced before, where we have triplicated waves and trouble imaging subsalt from 4 to 8 kilometer depth. The location of the CAG is indicated by the blue line. So first we compute the panel on the left, which is the space lag gatherer. And then we slant stack in this image space to obtain the angles. So one of the assumptions of the slant stack is smooth velocity fields and planar events. And as you can see, the events are not planar in the left panel. So slant stacking will result in smeared events instead of specular. So as you can see, I used 1 kilometer offset for the space lags in this case. And we can try to make it better resolved, the angles better resolved if we use less offset to make the events more planar. And here I use 0.6 kilometers offset. And you can see that, if I flip back and forth, that we avoid some of the artifacts between 4 and 5 kilometer depth. But if we reduce the size of the lag axis even further, here is 0.1 kilometers, you don't get additional resolution. And the events in the angular gatherers are not specular, they smeared horizontally. That's because we don't have enough offsets in the left panel, in the space lag gatherer. So in the ideal case, for horizontal plane event, you'll get a specular reflection. Here, a normal incidence angle. But for realistic models, such as subsalt, we never have this case. So we almost always violate the assumption of planar events and smooth velocity fields. Thus, the artifacts and the smearing in the angle gatherers for this method. So here's the comparison between two methods for the 6B model. And you can see that the point-in vector gives us a specular resolution, where the extended image method gives us smeared events. However, I put the question mark here because we also do a local smoothing in space and time for the point-in vectors, which can reduce resolution. And as I will show next, sometimes we don't get the correct angles for the point-in vectors because of the specular assumption that I make. So that's the next part, multipathing. when we have salt bodies, the waves triplicate. And we want to capture all illumination directions at each image point. So let's look at the simple example. Here I have one reflector at 2.5 kilometer depth and a low velocity Gaussian anomaly in the center of my model. So when I propagate the waves from the red dot, from the source, and it receives the green line, and I construct my angle gathers at the location indicated by the blue line. So when the waves propagate, you see duplications caused by the low velocity Gaussian anomaly. And we have separate branches of the wave field. And here the duplication, here we have 3 separate branches of the wave field and the pointing vector plotted on top. So here's the image of the reflector at the correct depth. And we also have an X-shaped artifact, as you can see from the different branches of the wave field, from the crosstalk. And the red dotted lines highlight the 3 different propagation directions that we want to capture at the reflector location. So as you can see that this model is symmetric. I construct my gather at the center of the anomaly. So we have normal incidence and 2 other angles that we would like to capture. So let's focus on the image on the right side for the extended image method. You see the 3 angles, normal incidence and 2 18 and negative 18 degrees angles that we capture. So that's good. But the pointing vector method only gives us 1 correct angle, which is the normal incidence. And that happens due to the symmetry of the problem. Because pointing vector averages all angles. And because of, like I showed before, the average angle happens to be the correct angle. And the red arrow point to the crosstalk events that we also capture. And you can see that they don't occur at the correct reflector depth. So we would like to avoid this. So let's disrupt the symmetry of the model a little bit and shift the gather slightly off the center. So we will still have 3 propagation paths that we would like to capture. But now they won't be normal incidence or symmetric around normal incidence. So the extended images method captures the 3 correct angles, but it also suffers from the crosstalk events indicated by the red arrow on the right that are not mapped at the correct depth. And the pointing vector method, in this case, does very poorly because it averages all the angles and doesn't capture the correct incidence angles at the image location, and also has some crosstalk events. So in case of multipathing, extended image method does better than the pointing vector method. However, I implement my methods efficiently, meaning that we can separate different branches of the wave field and capture pointed vectors for different branches to obtain the correct angles. But that will be very costly. So here I just focus on the efficient and practical implementations. Okay, so for the last topic, local heterogeneity in the model. So to analyze this, I construct a model that has a sharp velocity contrast. And for one source at 1 kilometer and one CG location indicated by the blue line. And when I propagate my waves, they will bend into the second layer. And constructing space-like gather on the left, you see 2 different slopes corresponding to 2 velocity layers. So slant stacking in that space, you'll obtain 2 different reflection angles, where only one will be correct, as indicated by the green arrow. And the red arrow points to the wrong reflection angle that we don't want to have. So this problem can also be avoided if we use a better local slant stacking. And the pointing vector method does pretty well in this case. But we also have to be careful because we also smooth it, like I said, in space and time. So if you smooth too much, then you can get incorrect angles. Okay, so this slide summarizes my, my talk. And like I said, the extended imaging method, the biggest disadvantage is the imaging condition cost. The computation and storage of the cross-correlation lags. But it does handle multipathing well. And the point and vector method is cheap and efficient because we do computations locally on the fly to propagate the wave fields. And it gives you specular resolution. And it seems to handle heterogeneity pretty well. But again, we have to be careful with smoothing. So looking ahead, I'd like to extend this work to anisotropic media. And one of the pitfalls, or one of the things that we have to be aware of, is converting from group to phase angles. That's for the pointing vector, because pointing vector gives you only group angles. And another one is formulating my angle decomposition problem as an inverse problem, where we can force a sparse solution and regularize illumination, and hopefully handle local heterogeneity. So on that, I'd like to thank two of my colleagues, especially Esteban and Francesco, and everybody at CWP. And I'll entertain any of your questions. Thank you.